Ready? So we're going to talk about vectors. So vectors is a confusing subject when you first talk about it, but it's not. I think it'll be fine, just like we did the other two stuff, matrices and complex numbers last week. So this says a vector is a line on the coordinate plane where the length of the line is called the magnitude and the direction of the vector is shown by its arrowhead. So really simply, an arrow is a vector. Doesn't make any sense right now, does it? Which is fine. Now, when we talk about this, it has two components that we aim at. It has magnitude and it has direction. So when we look at this a little bit more detailed, its magnitude, it's its length. Okay? And then its direction is, well, it's which way the arrow is pointing. It's telling you which direction it's moving. So you got to think back into where you probably have seen these before. Science. We dealt with motion. Vectors were used in motion, and direction points, and then the length of it tells you how strong the force is. So the length of the line shows its magnitude, or how strong that vector would be. And the arrow points in the direction that force would be moving. So this is going to be something as you're copying notes. Obviously, I don't want you to draw this. This is from the notes that I linked in for you. So where you would see something like this, or where you would think of this in the real world, a plane is flying along, flying north, okay? But there's wind coming from the northwest. So that looks something like this. Right? The propeller on the plane is forcing it, and we always say north is up on a paper, is forcing it straight upward, right? But there's some wind blowing on this plane. If you were looking from the ground, which direction does that plane look like it's going to be going? Does it go straight up? What does the wind do to it? Well, but when you think of this, these are vectors. The plane is trying to fly this way. That's its force vector moving it forward. But there's some wind pushing on it. So because we're trying to go this way, but the wind is blowing us slightly down and to the right. So if we actually look, if we were actually watching from below, our motion would actually look like the orange arrow. It almost seems like the plane is flying, sliding sideways. You ever seen something like that in the air? Birds and stuff like that. And this is just a graphical representation of something that we'd see in real life. So these are all just what we said. It almost seems like this plane is flying along this dotted orange line, even though the propeller and everything you want it to do is trying to drive it straight up to the top of our page, right? So that would be something that you would see vectors in real life. It's very applicable when you deal with physical science and movement and motion, things like that. Where we're going to look at is we're going to talk about operations and actually dealing with vectors once we take them out of the real world. Mathematics tends to strip away the application process and talk about more of the operations of dealing with them, other than the direct implication like a plane in the air and stuff like that. We look at just the numbers. So as you can kind of see here, we can actually take these line segments and everything else, and we can add them and subtract them, because the distance the plane, the direction and distance the plane actually flies from this is the orange line. Even though we're trying to find the plane this far with the propeller, but we're dealing with the force of the wind. Graphically, when you do this, you can add two vectors by joining them head to tail. So what that would look like, so it would look like something like this. If we had vector A and vector B and we wanted to add them together, we would have to take that and we'd have to preserve the direction and the magnitude of each one of these line segments with the arrow points. Okay, so A would stay in the same spot, B starts at the end of it, which is this way, and when we add those two things together, the orange vector is actually how far we would travel. You can think of it kind of like your plane analogy again. This time the wind's behind us. You ever ran with the wind behind you? Anybody that runs at all? You feel much faster, don't you? rather than running with the wind in your face and it feels like you're not going anywhere. Same idea. So this one actually pushed us along a little bit farther, and our resulting vector, this one, the long one, is actually what happens when we add them. It doesn't matter which order we do this in. We could put B and then A, and we actually get the same distance. And do you notice that this B and this B, they're the same length, same direction, because those are the two things we have to preserve when dealing with vectors this way. Now, like just about everything else we've learned about, if you can add it, that means you can subtract it. Because addition and subtraction are actually the same operation. Subtraction is just a shorthand notation for adding a negative. So they carry the same principles. They go together. Only thing we'd have to do when we draw this out is that we would need to reverse the direction of the vector we want to subtract. Meaning instead of its arrowhead pointing, so say we wanted to subtract B. Instead of its arrowhead pointing this way, pointing down that far, it would point directly opposite, same length, and it would look something like this. This was our A plus B, right? But notice that negative B extends directly out of B, opposite direction. That's where the arrowhead comes in. And this line segment's the same as this one. And that would be how we would subtract these things graphically. So vectors are line segments with direction and kind of angles of inclination that we need to keep track of. This is what happens in principle all the time with these things. Now, dealing with these just graphically like this or geometrically is tough because then you got to measure angles and you got to preserve length when you move things over because they're not always head to tail. In math, we like easier ways to deal with stuff. So we're eventually going to get out of this type of notation and we're going to deal with something different. So before I move forward, kind of see how this works. It's all about the direction of that arrowhead points and the angle associated with it. You have to preserve that as you went through. So let's talk about some calculations with this because this is a math class, not geometry anymore. We're going to take this, we're going to deal with some numbers with this. Okay, so the most common way to represent a vector is to break it into its X and Y components. So what we're doing is we're taking this line segment, because if you notice, these line segments are just kind of floating out here in oblivion. We're going to take these things and we're going to put them on the coordinate plane because then we can get numbers involved with it and we can do some calculations. So the easiest way to represent a vector, normal way, would be to break it into its X and Y parts. So which way on the coordinate plane does X go? It goes left and right. Which way does Y go? It goes up and down. It actually will help us preserve our distance, our magnitude of our vector, and it'll help us preserve our angle. So if you look at this vector A, what we're doing is we're breaking it up into two vectors, A of X, which is its X distance that we would travel from its starting point to its end point, and then A of Y, which would be the Y distance. So this would be kind of vector components of this vector. Now the way that we would notate this is it looks very similar to a coordinate for some of them. Some of them use more of a squared off parentheses, but we're going to stick with this one. This is vector A, and it has an X component of 8 and a Y component of 13. So what we're doing is we're taking vector A, and I didn't write A on here. The actual vector A is the one in black. But we're going to denote A by how far it moves from its beginning to its endpoint on the X and then its Y, because then I can take those two numbers and I can represent this vector anywhere in the coordinate plane. So representing vectors this way gives us an easy way to add and subtract them. We're going to see how that looks the same as what we were doing geometrically, but we won't have to draw them anymore. So all we need to do is add or subtract the corresponding parts of each vector. So we've got two vectors. We've got vector A and vector B. The X parts are 8 and 26. The Y parts are the 13 and the 7. So if I wanted to add these together and figure out what the resulting vector would be. Now, you got to think about when we add these things together, we're actually finding another vector. We're finding this orange vector that has its own X and Y components to denote its magnitude and its direction. So mathematically, we'd plug in our A, put our A and our B here. We're going to add the 8 and the 26. Because those are the two X components of this. I'm going to add the Y's, which is the 13 and the 7. So this tells me the resulting vector, if I add these two together, the orange one in our previous slides, should have an X component of 34, because that's what 8 plus 26 is, and a Y component, 13 plus 7 is 20. Which when we just look at this in numbers, doesn't seem to tie back into how does that correspond back to this orange line, which is really what we wanted to find when we added these things together. This is what we just did. Here's the 8, 13 vector. This is A. This one is B. And we're doing our addition. We put them tail to end. Sorry, nose to end. So this is A, this is B. There was our 26 and our 7. Now when we added them together, we got 34, 20. Now let's trace in on this. The resulting vector would go from here to here, right? It's going to have an X and a Y distance. Let me get it, my right tools here. To get there, it has an X distance here, then a Y distance here. It makes a triangle. What's our X distance? Our X distance is 34, and you can almost see that piece together. Here's your 8. This part is 26. That's the reason we added them together. And we ended up with the 34 on the bottom. We add the two Y components. We do find the actual direction and magnitude of that orange vector that we saw geometrically when we put them together. So the math does tie back into the picture, but it also allows us not to have to draw the picture every time to get to the resulting vector. We can just add them together and then use it. And sort of. And the hard part of this is we're not going to draw a lot of pictures because it's really hard for us to get, without a preset coordinate plane, to get those directions set up really well. We're going to focus mostly on the representation with the two component parts. Okay. So just real fast. Tell me what those are. I give you 4 vectors up here. And I'd like you to tell me what the resulting vectors X and Y components would be. Okay? All right, I put some answers up on the board. Kind of the same methodology we used when we added and subtracted complex numbers, where they had different parts and we added those parts together, subtracted them. Kind of the same thing with matrices. We added, subtracted the same elements together and kept them in order. This has different components. It has an X component and a Y component. And really, we look at this. So I put A and B, and we're adding them. So 5 plus a negative 3 gave me 2. And 9 plus 7 gives me 16. When we find this resulting vector, what we're doing is we're pinning this thing down on the end at 0, 0, and it tells me where the arrow points to, where it stops. So this one goes out 2 and then up 16. We can see that helps preserve its angle, which we'll eventually learn how to find later on. And it also preserves its magnitude, its distance, okay? And we can also use that to, those two components, to put different vectors together easily using a coordinate plane without having to measure any angles or anything else, because we could go from the endpoint and count out 2 up 16. We would know that would be the next vector that we'd want to add to it. We could draw our lines in between it. So I want you to think is what we're doing essentially is we're pinning this thing down at, say, 0, 0, and we put this at 8, 13, and then what we did is we counted out 26 this way, and then we counted up 7 from that endpoint. We could actually put all those things into the coordinate plane if we wanted to visualize this with both magnitude and direction preserved. That's what helps us with getting these X and Y components of this, okay? Everybody okay with the addition and subtraction? All right, let's carry on. Multiplying by a scalar. So first off, I've talked about scalars 3 times. Don't think I've defined it, okay? And it helps to kind of, when you hear the word scalar, scalar relates a little bit to a vector. So a scalar only has magnitude or size. And the difference from a vector, because a vector has direction as well. It has an X and a Y component to it. Scalars are just numbers like we've always worked with. 7, 12, negative 36, just a single individual digit number, integer, however you want to put it, rational number, that ends up being just a scalar. We multiply both the vector's parts by that scalar. So this works, this scalar multiplication. I want you to think back to what we did with complex numbers. If we had 5 times 2 plus 3i, we multiplied everything inside by 5 and wrote our result. So if we wanted to take a vector, say vector f here, negative 3, 12, and we wanted to multiply by the scalar of 4. 4 times f is 4 times this thing in its component form. This is, again, just like distribution. We're going to take this and we're going to distribute it through. What we're actually doing, if we were to look at the picture of this, is we're making this vector 4 times longer and preserving its direction as well. It scales the vector up, or it scales the vector down, makes it bigger or smaller. So we'd end up multiplying both parts, and the new one would be negative 1248. Now I know on something I linked to you guys on the notes in Canvas, it gives you a good way to expand that, but I can't draw a really good picture of that on our screen for us. But what I want you to think, I guess I can try. If this was our vector, that we started with, say this is our vector. When we multiply that thing by a scalar, say we multiplied it by 2, what's going to happen to it is it's actually going to become twice as long as the previous vector. I'm going to eyeball this. But by multiplying both components, it preserves the direction that we actually have. So it's like you're scaling it up or down that imaginary line of magnitude, and you're increasing its magnitude while preserving its direction. I want to practice the actual parts of this. Let's do a couple of these together because I think this is pretty straightforward. Let's see what we get. So I want to do 3a. So I want to make the vector a, I want to make its magnitude 3 times larger while preserving its direction. So mathematically what I would do, 3 times the vector 5, 9. So we're just basically distributing 5 to both of the components. I'm sorry, distributing 3 to both the components. 3 times 5 is 15. What's 3 times 9? 27. So now the new endpoint of that vector that starts at 0, 0 would be 15 on the x, 27 on the y. We could draw our arrow. 0.25c. When we multiply by a fraction, we're actually dividing. So technically right now we're dividing vectors, dividing the vector by a scalar, but we're gonna relate it back to multiplication, okay? So 0.25 times c, so that's 36 and negative 5. So what is 0.25 times 36? 9? And 0.25 times negative 5. Negative 1.25. So we can have decimals in there for part of that length as part of one of those components as well. All right, negative 4b, that's negative 3.7. So a negative and a negative gives us our positives. So that's 12 and negative 28. Also, one thing of note as we go through this, because we've talked about factoring a lot, you're never going to pull common factors out of the components because that'll change the magnitude of that vector. Okay, if we see that by multiplying it through, we're actually making the vector longer, even though it's in the same direction. If we take those common factors away, we would shrink it, so we can't do that. So there's no factoring in between components, okay? So how do we feel? Down, middle, thumbs up, thumbs middle, thumbs down. And right now I want you to focus on the operations itself. Once you get those down pat where you're not thinking about those as much, and we get into a couple of the, like Tuesday's example assignments, you'll see how these things kind of get pieced together a little bit more. All right, so magnitude. What we've looked at so far when we've looked at these vectors, so let's look at one that we've got here. Let's look at, let's take 5, 9. We've talked about that we can graph this thing. So it comes out here to 5 and then up 9, right? And we end up with our vector starting at 0, 0. That one points in that direction. What we've been playing with so far is we've been playing with the two parts that make up where this vector actually goes. We've been playing with the x component of this and the y component of this that make up this angled line. Now, when we talk about magnitude, the magnitude of this vector is actually this part right here. We want to know how big is that line, okay? So first things first, let's talk about notation. So 2 ways you could possibly see a question ask you for magnitude. So the magnitude vector simply can be thought of as its length. The notation for magnitude can be either 2 vertical bars like this, kind of looks like an absolute value sign, right? Or it can be double bars on either side. So a little explanation of this. Absolute value means we use absolute value to represent distance. Because can distance ever be negative? No, we talk about driving cars. You're always driving somewhere, right? Even if you're driving back home the exact same way you came, it doesn't take the miles off your car, it puts more of them back on. Okay? So, but that's also what we're kind of looking at here when we talk about magnitude. We're looking at the distance of this line itself. The reason the double bars come in is to separate the notation so you don't confuse it with an absolute value problem and you understand that it's supposed to be magnitude. Unfortunately, this is where some information can get mixed up and you can see the single set or the double set. So you got to pay attention to whether you're playing with vectors or not, okay? So we want to find the length of this line. Any ideas? So I'm going to erase this picture because I have it down in here. If we look at this thing in component form, and I took this one back to where we had the one that we played with before, I want to know the length of the black line in that segment. What shape am I playing with here? If I highlight it out, what do the 2 purple parts make? Like if I put all three of these things together, forget about the arrow points. What shape is that? Say it really loud. You know I can't hear. Anybody? This right here.
The triangle.
What type of triangle? It has a special angle in it.
Right triangle.
Rule of note, as we go through and learn some of this stuff, what's the most important formula for right triangles? Anybody remember the guy's name? Pythagoras. And as you kind of extend through, we talk vectors and a lot of stuff, trig and everything else. It all really stems from the Pythagorean theorem. We can find the length of that really easy because that's a right triangle. How do you find that length? We're using the Pythagorean theorem. What's the Pythagorean theorem? Which part's c squared? The 8 to 13 or the magnitude? The magnitude. Does it matter which one of these is A or B?
No.
Nope. What's 8 squared? 13 is 169, right? And this is why I had my calculator out that's on the other table over there that I can't reach. So we're going to, I forgot to write the squared on this, I'm sorry. Because this number is still squared. So 169 and 64 is 233. How do I get rid of the squared on that magnitude? Square root it. So it's the square root of 233 is that magnitude. That's its length, right? So let me do a little bit of digging with this one. See if we need to mess with this at all. Nope, 233 doesn't have any perfect squares in it. The only thing you have to be cautious with, the time we get a square root, you're guys are going to be expected to simplify it, which when we get one, we'll double check. But that one doesn't do anything, so that would be exactly how to write its magnitude. What is that about equal to? Anybody actually plug it in? 15.26. Which makes sense because the magnitude should be the longest length inside. It's the hypotenuse of this triangle that we're actually dealing with that's formed. So it should be the biggest one. So it actually leads us to a formula. The magnitude can be found by taking the square root of the x component squared plus the y component squared. That's how, and that's actually the distance formula, which we're plugging through into a coordinate plane. Now, easiest way to get confused with this is getting mixed up between the two components that we make up when we write our vector in component form and its magnitude, okay? Because you can write it as magnitude and direction, which is an angle, or we could write it as two component forms. And we'll get to magnitude and direction as an angle in a little bit. So what I want you to do, wait a minute, where'd my problems go? Oh, they're there. Find the magnitude of each one of those vectors in component form. So the answers that I'm looking for here, I want you to tell me the magnitude of A, the magnitude of B, and the magnitude of C. And I wrote both of them up there, square root and the about. This is ACT prep, so I'm unsure how they're going to write the answers for you. We'll see some as we do some practice later on this week with it. But it never hurts to have both representations at least written down on your paper, especially if we're talking ACT, you're going to match an answer. You know, run them both down real fast and make sure you can see it. So, and rounding, I'm perfectly fine with 2 places if it's something you're turning into me, okay? All right, one more that I want to do together. Everybody okay with this? I'm sorry. The magnitude is Pythagorean theorem, okay? That's why we break it down as X and Y components, so we end up with a right triangle again. We're going to get a bunch of that, okay? All right, last practice problem. I want to kind of put all this together for us. So I say, given point P and point Q, I want to write the vector P to Q in component form, and I want to write its and I'm going to find its magnitude. So what I'm actually going to do is I'm going to kind of graph this and put this together for us. So I'm going to draw X and Y so I can graph it. Try to make it a little bit prettier than before. No promises. And we don't need to go very far because we only need to get to -2 and 1. So 2 on each axis should be fine. But the way this is started is we have coordinates here instead of vectors. They're really tough to tell the difference with, okay? So our first point is at -2, 1, which is back 2 up 1. So this is point P, and point Q is at 1. Try to make them even so it matches up. is at 1, -2, which is down here. So this is Q. And what we're saying is there's a vector between those 2 points. One of them's the end point. One of them's where it begins. One of them is where it ends. So where does our vector PQ begin? Does it begin at point P or point Q? Begins at point P, because that's the one that's first. So there's actually a vector here. And it starts at P, and it goes to Q. Now what I want to do is essentially what this is asking us to do is to standardize this. When I told you we were finding our vectors in component form, what was the point that we always started this end on? If we were in the coordinate plane, we always started this at 0, 0, so they could be standardized and we could add them together and see it. This one's not, and essentially what I'm doing with these operations is I want to put this in the right spot and figure out how long it is. So I essentially want to move point P from where it's at to the origin so I can find the magnitude. That's what we're kind of doing when we write component form. So component form for this. Let's look at it on the picture and see if we can figure out what we're going after. So we want to go from here to here. So the X would be this way. So this is our X component. And our Y would go down from there. So we need to know the lengths of those things. We're going to make the outside edges of the right triangle. How long is the blue line? Does anybody know? We could almost just count it. This process kind of ringing back to something you did maybe back in like 6th grade. And you found the components between 2 points and you actually went through and like counted out slope. It's almost the same thing. But you can count these out and find these components. We're going to talk about how to do this mathematically, but we want to be able to see this on a picture. It's 1, 2, 3. This component is 3. Positive or negative? Positive, because we're traveling from the left side to the right side. So we know that this distance is the 3. The Y component of this, so let's actually write this out piece by piece. Here's PQ, and we're going to write its vector components. The first one is 3. That's its X part. What's its Y part? Well, first off, is it going to be positive or negative? What do you think? Is it going, we're right here now. Are we going down or are we going to go up? We're going to go down. So that's got to be negative. And how far down? 1, 2, 3. So that one's also -3. Let's say we didn't want to draw the picture or the numbers were really big and we didn't want to have to count that many. How could we use the numbers to help us find that?
You could just do whichever one to 0.
You know, ask that question, I knew I wouldn't be able to hear the answer. Be really loud.
Like you have to use the one number until it reaches 0. You know?
I think I know what you're saying.
Yeah, I had a
Because I want to figure out a way to use this number and get them to be 3, right?
2 to 0, then 1 to 0. That's good.
If you take the absolute value of each component and add it together, that will always equal the overall component. You get what I'm saying? What's the absolute value of 2 plus 1? Because it's a distance. Is distance ever negative?
No.
So that's 2 plus 1, which is the 3. Now we need to be careful with the other one because we're traveling down, so we kind of need to get the picture out of it as well, okay? Let's find its magnitude, and we'll come back to that part. How do you find magnitude now that you know this? So the magnitude of the vector PQ is going to be the square root of 3 squared plus -3 squared, which is Square root of 18. Now, this is the one that I want you to be careful with because this is where I think they probably get you on the ACT. That has a perfect square in it. Meaning, I bet you if they were to write this answer, they're going to write this. Why would they write that? Because anytime you have a square root with a number underneath it that doesn't have a perfect square, you got to hunt for factors that are perfect squares. 18 is 9 times 2. So you can take the square root of 9, then multiply it by the square root of 2. The square root of 9 is the 3. Square root of 2 stays underneath. And we'll throw some more practice like that around because it's something that you've seen here and there in answers. It's probably